Welcome back to Math 451. We're going to pick up where we left off last time as we were discussing numbering system and rational and irrational numbers and whole numbers. And we're going to continue on with some preliminaries that are supplementary to your book, looking at counting and a principle called induction. So counting, let's start with that. What do you need to count for? You've known how to do that for a long time. Well, we're actually going to be building what are called counting formulas. The formulas that we'll look at are necessary to predict the computational requirements of an algorithm, a typical mathematical algorithm. Often, as we set up loops and nested loops to accomplish these algorithms, the number of floating point operations, as we are going to call them soon, will be proportional to a counting formula. And you can build a prediction of how long the algorithm will take and even develop something like a little progress bar that will give your user of your algorithm some idea of how much longer it has to go. Well, that's only possible if you can predict in advance accurately how long your algorithm is going to take. And these counting formulas are going to help us just do that. So let's start with the first of many. This one will come back and we'll need it again later, so don't forget it once we go through it. But we're going to pose a problem that was posed, as legend indicates, to an elementary school student whose name was Carl. And this student was a bit obnoxious, and he was sent to the back of the room by his instructor and told to count all the integers from 1 to 1,000, actually to add them all up, to add 1 plus 2 plus 3 up to the number 1,000. Well, the instructor thought that'd keep him busy long enough that he could finish his class, but unfortunately it was only a few minutes later when Carl came out and had an answer for him. He really couldn't believe it until he looked at it, and it turned out he was right. He came up with the answer 500,500. Well, let's do this problem that Mr. Carl Friedrich Gauss came up with, or the solution he came up with in elementary school, and we'll do it in general. So instead of adding just from 1 to 1,000, we're going to add from 1 up to any arbitrary ending integer. So let's go ahead and add all integers starting with 1 up to some arbitrary stopping value, which we will call n. Now this algorithm, as I indicated, is going to be a basis for looking at algorithmic efficiency. And what Mr. Gauss did, is what we will do also, is write this formula down in two ways. First, we'll write it the way he was posed by his instructor. Add up all the integers from 1 to some stopping value, which in his case was 1,000. What Mr. Gauss did is he turned the formula backwards and said it has to be the same answer if you add up the same numbers backwards. But if you do that and then you add in columns, on the left, you'll get S sub n plus S sub n is 2n. And on the right, you're going to get a series of additions that will always be n plus 1. So that first column is 1 plus n. The second column is 2 plus n minus 1. That is n plus 1. And similarly, all the way to the last one, n plus 1, is still n plus 1 over here on the far right. So we could write that as n times n plus 1. That's what multiplication means, is repeated addition of the same number. Now we can divide both sides by 2, and we come up with a formula for the sum of the first n integers starting with 1. So that was how Carl did that. I don't think I'd like having a student quite that smart in my class. It'd be hard to keep control of him, but we'll put QED on it, which means we're done and we've solved it. We might like to have a simpler way of checking the validity of a formula like this instead of deriving it from scratch. Now, sometimes you're suspicious you know what the correct counting formula is, but you really do need to prove it. So we will use a new method called proof by induction. It will not only be simpler, but it has some analogous behavior with other computational tools such as recursion. We'll get to that later. But the way it works is you take a candidate formula that has an n or some other parameter, and you plug the lowest possible value you can into that formula. So in our case, n equals 1 would be the smallest value we would use. So let's, for starters, take our formula that we're hypothesizing and plug in a 1 everywhere you see an n. What does that mean? It means I'm just adding the number of 1. There isn't any addition to do. It stops at 1. And see if that is equal to 1/2 times 1 times 2. Well, it certainly is. You just plug the formula in and you get 1 on both sides. Notice I have renamed this variable to be s sub 1 of n, and I can name it anything that I want, but we'll find that a little handy later. So now the trick is to assume that the formula works for any arbitrary value of n, which we'll call s sub 1 of n, and rewrite the formula back as s sub 1 of n plus 1 now, rather than s sub 1 of n, as being the sum of the first n plus 1 integers. So it's the same form, we just added one more term to it. Well, we could easily break the right-hand side into two groups. The sum from 1 to n, and then add this final integer at the tail end of it. But the first n numbers is our s sub 1 of n, therefore I plug it in. We get this particular expression. We can factor out n plus 1, and we end up with n plus 1 times n plus 2 divided by 2. Look at the form of that. It is the same form that we had for s sub n. We have just replaced the role of n with n plus 1. So you put an n plus 1 here on the left, put an n plus 1 here, and put an n plus 1 here, and you will get 1/2 n plus 1 times n plus 2. So we've proven the formula works for n plus 1 if it works for n. But that means it will work for n if it works for n minus 1. And it'll work for n minus 1 if it works for n minus 2, and continue all the way down until you check to see if it works for the very first n, which it does. And therefore we have a proof by induction that that formula is correct. Okay, so I think it's time to give one of these a try, and we can stage a homework problem here worth 20 points. And using our newer notation with subscripts, we can define not only s sub 1 of n, but we could define s sub 2 of n as being the sum of the squares of the integers, or we could define s sub 3 of n as being the sum of the cubes of those integers. And I would like you to prove that this relationship works. So in other words, whatever you get by summing up the n integers, if you square that, you would get the same thing as if you summed the cubes of those same integers, again starting with the number of 1. So we'll define this arbitrary term called s sub k of n as meaning 1 to the kth power plus 2 to the kth power all the way up to n to the kth power. And we'll see if we can't prove that the sum of the cubes of consecutive integers starting with 1 is equal to the sum of the integers directly and then squaring it after you've added them up. So the hint here on accomplishing this is, first of all, use induction. You'll find it a whole lot easier than trying to prove that thing directly. And use the formula for s sub 1 that we derived on the previous page. Go ahead and plug it right in there. We've proven it, so it's yours to use. And see from that alone if you can't prove that that relationship exists. So we will give you a chance to give that a try, and that will end our session for today. We'll see you next time as we move into the actual textbook itself.